Hey everybody, Mr. Murphy here. We're going to talk about the Hardy-Weinberg equilibrium. So here's the basic premise. In a sufficiently large population, absent any influencing factors, a trait should find an equilibrium of frequencies of its various alleles. So breaking that down, what that's saying is that if we have a population and there's a particular trait and there's different versions of that trait, let's say, between different individuals within that population, if we were having no selective forces whatsoever, if having one version of the trait was exactly the same as having another version of the trait, we would expect that generation by generation, the frequency of those two different alleles, the different alleles that code for that trait, let's say a dominant allele and a recessive allele, in the entire population really shouldn't change. There should be no, since there's no influencing factor, we shouldn't see any increase or decrease to the amount of one versus the other. To help with that, I'm going to establish sort of an example here. And that is this idea of the ability to roll your tongue. So since I'm not with you right now, I'm just going to make up some numbers. And let's say we survey a classroom of 28 people, and we find that 23 of them can roll their tongue and 5 cannot, which is probably approximately what you might find in that size of a group. Most people can roll their tongues. But hopefully we can agree that the ability to roll your tongue does not have any actual influence on your ability to survive or be selected for to one day reproduce. Anyway, the point is that it should be expected. We shouldn't see any shift in tongue rolling ability, because within the human population, if we expand this from 28 people to the entire globe, we expect there to be a certain number of alleles, the dominant alleles that confer the ability to roll your tongue, and a certain number of alleles that do not. And that's the recessive alleles, the ones that fail to produce whatever protein is necessary to give us that ability. We would not expect that to really change, because we have homozygous dominant, we have heterozygous individuals, and we have homozygous recessive individuals, and everyone's kind of, continuing on future generations of the population with no respect to tongue rolling ability. And for that reason, if the population was large enough, we would just expect it to stay the same. Now, if the population's too small, then random chance and stuff like that could cause it to deviate. But hopefully we can agree that human population level, we really shouldn't see too much of a change. Now, if we have 28 total people, and remember that every individual is going to have 2 copies of the gene, either coding for the ability to roll your tongue or failing to code for that ability, the recessive allele. And so if we think about what these individuals actually have, these non-rollers, we know they're going to have little r. They have 2 recessive copies, so each of them will have 2 of these. But the people who can roll their tongue, if we were to look around a classroom, we really can't know what their genotype is. And the reason for that is because they could be homozygous dominant, like this, or they could be heterozygous. And we would have no way of being able to differentiate, because as long as you have one functional copy, then you have the capability to roll your tongue. There's no, in this simplified example, there's no middle ground. So what that means is, if we look at the total population of 28 people, that means that in terms of the alleles in that gene pool of 28 individuals, there are 56 total alleles. So that's our sort of setup example. Now I'm going to return and talk a little bit more about what Hardy-Weinberg tells us about genes that have this situation. So this is named for 2 dudes a long time ago, like everything. And there are some assumptions that I want to cover. So in order for a gene to be following what is called Hardy-Weinberg equilibrium, following this sense of not changing generation to generation, we first off have to be looking at a diploid organism. We have to be looking at organisms that sexually reproduce. Generations are non-overlapping, generally not a problem for people, but animal kingdom gets weird. Mating should be random with respect to this particular trait, which means no selection, which also gets reiterated later on. The population size needs to technically be infinitely large, and I know that's weird and obviously unrealistic, But when a population is sufficiently large enough, we should see the allele frequencies staying the same, or at least close enough to suggest that there's no selection. Allele frequencies are equal across the sexes, so the math behind this principle doesn't really work if we start looking at things that are sex-linked and such, because that throws off sort of the subsequent generation likelihood of different traits appearing and such. And then finally, there's no migration, gene flow, admixture, mutation, or selection, which is a pretty loaded statement. Basically, the point is that in order for there to be an equilibrium in the frequency of the different versions of this allele, there needs to be nothing, just no thing affecting the prevalence of it. Okay. If a trait is in what is called Hardy-Weinberg equilibrium, it is expected that the frequency of the dominant allele and the recessive allele should remain constant. Notice that's not saying, the frequency of heterozygous and homozygous recessive, none of that, but just that when you take the whole population and you've studied all of their individual alleles, the frequency or the percentage that is dominant and the frequency or percentage that is recessive should stay the same. Now, normally, we can't know allele frequencies of, a classroom, for instance, because of the heterozygous individuals. So a bunch of people in the room right now are able to roll their tongues, but they may also carry a gene that is recessive. But because they have a dominant one, they can do it. So we don't know how many people in the room are heterozygous versus homozygous dominant. However, because tongue rolling largely fits Hardy-Weinberg equilibrium, we can actually use a statistical method to figure out how many individuals in the room probably are heterozygous. Now, of course, using this as a classroom level example, we aren't even close to the population being infinitely large enough. But we can stretch that rule for now just to practice this. There are two equations, and here they are. And it's important to take a second to wrap your heads around what these different variables actually represent. So the first one is P plus Q equals 1, where P is the frequency of the first version of that allele, which is typically our dominant version, and Q is the frequency of the recessive allele. Now, when we say frequency, that just means the total number of dominant alleles divided by the total number of alleles in the classroom. And Q would be the total number of recessive alleles divided by the total in the classroom. Now, if we take a second and return to our data here, we can't actually do anything with this first equation yet. And the reason is because I don't know what these people are. These 23. I don't know how many are big R, or big R, little r, so I can't look at how many total big R's or little r's we have. I know we have at least 10 little r's because of these 5 people, 5 times 2. You can check my math on that. But I don't know anything about these people. So that's why we have a second equation. And that equation says P squared plus 2PQ plus Q squared equals 1. And what that actually represents is the 3 different possible genotypes. P squared is homozygous dominant. 2 times P times Q is the frequency of heterozygous, and Q squared is the frequency of homozygous recessive. With these two equations, if we know that a gene or an allele, a trait rather, is in Hardy-Weinberg equilibrium, and we know just a little bit of information about the population, we can figure out what the rest of the population must be in order to support this allele being in equilibrium. So let me show you what I mean by that. When we look at the data and we see that we have 23 tongue rollers and 5 non-rollers, we can't do anything with this first equation. Like I said, I don't know the total big R's or little r's. But if we look at the second equation, I don't know how many homozygous dominant individuals there are. I don't know how many heterozygous individuals there are. But I do know, because they can't roll their tongues, how many people in the room are non-rollers. So I can figure out what the frequency is of this genotype in the population. And the frequency of that genotype is going to be equal to Q squared. So Q squared equals, and I know that that is 5 out of the 28 total people. So that gives me a way in on evaluating these numbers. And if I look at this and I do 5 divided by 28 and I get, well, it's 0.18. Okay, well, we'll stick to some sig figs, I guess. Or not, I don't know. Don't worry about sig figs. So I get 0.18 is q squared. Now, if my ultimate question here was, I want to know how many people in the room of these 28 people are heterozygous. Ultimately, what I'm going to want to solve for is here where it says 2pq, which means I need to know what q is and I need to know what p is. But I already know what q squared is. And we can just use math now because I know that q is going to be equal to the square root of q squared. So it's going to be equal to the square root of 0.18. And so again, we just bust out our calculator, square root of 0.18, and I get 0.42. So what that means is that within the room, 42% of the alleles are actually recessive alleles. That might seem high given that there's only 5 people who are non-tongue rollers. But the reason why it must be this number, again, we're just forgetting about our population size assumption, but the reason why it has to be this number is because in order for the population to sustain this frequency of the homozygous recessive allele, there would have to be this many total recessive alleles in the population. Now, many of those are going to be within heterozygous individuals. So now I know what Q is. Knowing what Q is allows me to use the first equation because these two equations can be used in conjunction with one another. And so if I know that Q is 0.42 and I know that P plus Q equals 1, then I know that P is equal to 0.58 because 0.58 plus 0.42 is 1. And that makes sense also because this is what fraction of the total alleles are dominant plus what fraction are recessive, and total, since those are the only two options, that should equal 1. Knowing that now, I can unlock any other piece of information about this population that I want. So for instance, in this example, I said I want to know how many people are heterozygous. Well, I can do 2pq and actually just multiply that out. So 2 times 0.58 times 0.42. That's 2 times p times q. And math. I get 0.49. And that tells me that 49% of the individuals in the room are heterozygous. Now, if my question was how many people, then we can't stop here because all I gave was the fraction of the population. So I need to actually then take my 49% and multiply it by the 28 people in the room. And I see that it's about 13.7 people. They frown on, fractions of people in general. So we'll just call that 14. And that tells us then that about half the room is going to be heterozygous, plus 5 individuals in the room who are homozygous recessive, and then that leaves 9 individuals in the room who are homozygous dominant. It tells us nothing about who's who, but in order to sustain this allele in a consistent equilibrium, this would be the rough breakdown of the population in order for that to stay true. That's what this does for us. That's one application, and it's the application that College Board loves to ask about. So yes, these equations are on an equation sheet that they'll give you, and yes, there are math questions that they ask you on the AP test. We don't really need to sweat it, but that's the typical kind of question they give. They tell you a trait, and they say, hey, here's a particular trait. It's in Hardy-Weinberg equilibrium, and here's how many individuals show the dominant trait, and here's how many individuals show the recessive phenotype. And then they ask you to find how many individuals were heterozygous or homozygous dominant or something like that. The key to these problems every single time is these recessive phenotype people, because those or that population is the group that we know about. We know what both of their alleles are, and therefore nearly every Hardy-Weinberg problem I've ever seen on an AP test has been, okay, start with Q squared, find Q, find P, and then solve for whatever they actually asked for. It's very, very similar almost every time. However, there is a second type of problem that you can do, and that's going to be what the problems on the practice that I'm giving cover, which is that you can test for whether a population's trait is experiencing Hardy-Weinberg equilibrium. And the way to do that is if we knew what the starting conditions were, if we have the ability to calculate P and Q and all of the things, and then we're given information about the next generation, and we can solve for P and Q again. Now we can look and see whether the total population's gene pool has shifted in some way. If we saw an increase in P and a decrease in Q, then that would tell us that we are not in equilibrium. It doesn't tell us what's happening, but it suggests that there's some sort of selection or some sort of reason why this population is experiencing a shift in the prevalence of certain traits. And that's a valuable tool. It gives us a statistical way of analyzing that, yes, a population is currently experiencing selection, which is a great tool for understanding, the different properties of the environment and how that might be influencing the prevalence of different traits, which is causing selection, which is driving evolution in a population. So that is what Hardy-Weinberg equilibrium is all about. And I know that's pretty dense and thrown at you. So we're going to practice. And then when I'm back, we will look at it some more and we'll see if we're having any problems. It's not really all that hard, and once you sort of get it and it clicks, it's like the easiest kind of problems you could ever do. So there you go. I hope that was tons of fun. Enjoy.